Hello everyone, this video is on abstract algebra, introduction to groups. Now groups are algebraic structures, so our first topic is algebraic structure. Algebraic structure. An algebraic structure consists of two things, a set and operations defined on the set. To build any structure, we need two things, objects and algebra. The set consists of objects and the operations defined on the set gives algebra to the set. Now take any set. To manipulate the elements of the set, to combine two elements of the set and to again get another elements of the set, we define operations on the set. For instance, the set of natural number n. We add any two natural numbers to again get another natural number. For example, 2 pence plus 3 pence gives 5 pence. Here n is the set and the operation addition is the operation. So the set n along with the operation addition is an algebraic structure. So the operations defined on the set gives algebra to the set. Next topic is binary operation. In the example, the operation addition takes two operands. Such operations which take two operands are called binary operations. Groups. A group is an algebraic structure, one of the simplest type of algebraic structure. It consists of a set and a binary operation defined on the set, such that the set is closed and associative, has an identity element and an inverse of each element under the given operation. For example, the algebraic structure Z plus, the set of integers Z and the binary operation addition forms a group, since Z is closed under addition, is associative under addition and has an identity element 0 and has an inverse of each element under the addition. Next we study the motivation behind the groups. What led to the study of groups? For that we consider two equations. X minus 3 equals to 2 and x plus 3 is equals to 2. The first equation has a solution in n plus, x equals to 5. But the second equation has no solution in n plus. But the second equation has a solution in Z plus. And the solution is x equals to minus 1. So, why does the second equation has no solution in n plus but has a solution in Z plus? What guarantees the solution of an equation in an algebraic structure? For that, we study the properties of algebraic structure. Thus, algebraic structure n plus is not a group, whereas the algebraic structure Z plus is a group. So, any algebraic structure that is a group has a solution of the equations defined on that algebraic structure. And the solution of equations, this motivated to the study of groups. Next we discuss the properties of groups. And note that the properties of groups follow order. And the first property is the cancellation law. To prove this property, we use the axioms of group. Now because A belongs to G and G is a group, the inverse of A exists. Suppose A prime is the inverse of A. To prove this property, to cancel out A on the left from both sides, we operate on the both sides on the left with the inverse of A. Then A inverse asterisk A is E, identity element, and B E is B and C E is C. So we are left with B equals to C. And likewise, to prove this right cancellation law, we operate on both sides from right by A inverse and we reach B equals to C. The second property is the uniqueness of the identity element and the inverse of each element in the group. That means there is only one identity element in a group and each element has only one inverse element in the group. The proof of this property directly follows from the cancellation law, and there are different versions of the proof. It's very simple, so we don't discuss it here. The third property is the equation x equals to b has a unique solution in G. So it all came down to the solution of equation. As discussed earlier, this is what motivated the study of groups. First, we saw that the equation has a solution. The solution of this equation is x equals to some value. We need x alone on the left hand side. For that, we eliminate a. To eliminate a, we need its inverse, and G is a group guarantees the inverse of a, and because the inverse elements are unique, suppose a prime is the inverse of a, next we operate both sides by inverse of a. Next we apply the associative property of group, then apply the property of inverse. We have E, identity element. The identity element is guaranteed by G as it is a group, and we came down to this solution. The solution of this equation is x equals to A inverse B. This is the solution of this equation, and A inverse B lies in G is guaranteed by the closure property of group. Therefore, this equation has a solution in G, and the solution is x equals to A inverse B. So what guaranteed the solution of this equation? These four axioms known as group axioms. These four axioms are summarized in groups. Next we show that the solution is unique. To show the uniqueness of the solution, as usual, we suppose two different equations of the solution, and we show that these two different equations are in fact the same solution. So let x1 and x2 be two different solutions of this equation. Then, because x1 and x2 are the solutions, they must satisfy the equations. Therefore, ax1 equals to b and ax2 equals to b. Then, this quantity equals to b, this quantity is equals to b, therefore ax1 equals to ax2. This gives us x1 equals to x2. Why? By what property? By cancellation law. So the uniqueness directly follows from the cancellation law, and the equation ax equals to b has a unique solution in G. Also, without the loss of generality, the equation ya equals to b has a unique solution in G. The first property is AB inverse is equals to B inverse A inverse. That is, the inverse element of AB is B inverse A inverse. By definition of inverse element, we must have AB asterisk inverse element of AB is equals to identity element. We prove this property by proving this definition. So we have AB asterisk inverse of AB. By continuous application of associativity property, we get AB asterisk B inverse A inverse equals to E. Therefore, the inverse element of AB asterisk AB prime equals to B inverse A inverse.